Welcome to the Grade 10 unit entitled Introduction to Electronics. In this unit, we're going to explore the study of electronics, and we're going to look at the application of electronics in terms of a number of electronic components. Well, we're going to be looking at vacuum tube devices. This is a very interesting area of study because vacuum tubes were used in the early days of electronics in a lot of electronic appliances. And it's very interesting to sort of go through the physics behind these devices because it gives you an idea how electronics has evolved over the years, but how electronics still uses the same basic principles of controlling the flow of electrons. Well, let's define electronics. Electronics is the branch of science that deals with the study of flow and control of electrons. And this is what we know as electricity, the flow of electrons. And it's also the study of their behavior and their effects in vacuums, gases, semiconductors, and with devices using such electrons. Now, this control of electrons is accomplished by many of the devices we're going to have a look at in this unit. And these are devices that are able to do a number of things in relation to electrons. They're able to resist, they're able to carry, select, steer, switch, store, manipulate, and exploit the electrons. And so electronics is indeed the study and design of systems that use the flow of electrons through components such as semiconductors, resistors, and capacitors. And so in terms of what thermionic emission is, this basically involves you heating up a substance by passing a current of electricity through it. And when that substance becomes very, very hot, then what happens is that the electrons in that substance literally evaporate off, and they actually come off the component, and you've got free electrons which are emitted from that heated element. So this heated element, which is very hot, it's red hot, the heat which is generated by passing a current through a very high resistor, which means that it resists the flow of the electrons, and as a result of that, it emits the electrons because of the fact that the electrons are able to jump off this element because of the very high temperature. Then this is what's called thermionic emission. So this is a hot filament, and these are the electrons which are emitted from that hot filament. Now, another thing which we need to look at, and which we are eventually going to get to in a moment, is to describe the behavior of vacuum tubes. And so this is an example of a vacuum tube. The other learning objective is that we're going to describe the function of a cathode ray tube and describe the use of cathode rays. And this is a cathode ray tube, and we're going to have a look at how it works as we go through the course. So you can see here that what we have is a cathode, and that emits electrons when it gets heated up. And so those electrons go past an anode which attracts the negative charge electrons, and it's able to focus those electrons onto the screen. So we're going to be looking at the function of cathode ray tubes, in particular in certain devices like, for example, television sets, and seeing how the design of a television set allows us to get the images that we have on the set. And that's due to the use of cathode ray tubes within those television units. Thermionic emission is in fact a process of emission of charged particles. And these charged particles are known as thermions, and they're emitted from the surface of a heated metal. Now, these charged particles are normally electrons. And in fact, the rate of emission, in other words, the number of electrons emitted in 1 second, is affected by a number of factors. And these factors are as follows. The temperature of the heated metal. The greater the temperature of the heated metal, then the greater the emission of the electrons. So in other words, the emission rate of the electrons is directly related to the temperature of the resistor. Also, the surface area plays a part. In other words, if you have a large surface area, then the rate of emission of the electrons will increase. Now, in vacuum tubes, we basically have a tube in which all the air has been removed. We tend to refer to vacuum tubes as thermionic diodes. Now, the reason why they're called diodes is because a diode is an electrical component which has two electrodes, a positive one, which is called the anode, and a negative one, which is called the cathode. These are used for what's called rectification. So what is rectification? Well, rectification is the conversion of what's called an alternating current, an AC current, into a direct current, a DC current. So here on the right, we have a vacuum tube, or to be more specific, we have a thermionic diode. And here you can see in terms of the diagram, it consists of a glass tube which encases a cathode, which is the negative electrode, and an anode, which is the positive electrode. So to summarize, we can say that vacuum tubes are tubes with no air, and that in terms of describing thermionic diodes, we can talk about a thermionic diode as an electrical component which has two electrodes, one of them being positive called the anode, one being negative called the cathode, and they're used for rectification. And by rectification, what we mean is converting an alternating current, an AC current, into what's called a direct current, a DC current. So you would have come across alternating current and DC current when you studied the unit on current electricity. So this would be an example, a very simplified example, of what a diode would look like in terms of a thermionic diode. And here you can see you've got the cathode, you've got your tube enclosure here, which is an enclosure which contains an environment where there is no air, there's a vacuum inside of that tube, and then you've got your anode at the top. So by heating the cathode, what you get is the emission of electrons which are negatively charged, and they're attracted to an anode plate which is positively charged. And so as a result of that, you get a stream of electrons being emitted from the cathode towards the anode. So a thermionic emission is applied in thermionic diodes. A diode is an electrical component that only allows current to flow in one direction. And electrons can only be released from the tungsten filament when it is hot, and it moves towards the anode, which is connected to the positive terminal. Also, electrons are not allowed to move in the opposite direction because no electrons will be released from the anode. Remember, the anode is positively charged. It's essentially attracting the electrodes from the cathode. Also, the electrons can only move from left to right because, as we mentioned previously, the electrons cannot move from the anode in the direction of the cathode. So we only have one direction movement. So let's have a look at an X-ray tube. Well, an X-ray tube is illustrated in this diagram. And if you look at the X-ray tube, you see something quite interesting, because in the X-ray tube you have a filament which is being heated up to release electrons. So this is acting a bit like the example that we saw in the previous diagram, in the sense that this is acting like a cathode which is emitting electrons. And then you can see that this side over here in the actual tube is a copper anode, so that's attracting the electrode. So essentially what we have in an X-ray tube is the generation of electrons from a cathode which is being heated up. And these cathodes are then being attracted to an anode which is positive, in this case a copper positive anode. And when the electron beam hits this target which is on the copper anode, and this is a very heavy metal target, then what happens is X-rays are released. So what we get in effect is an X-ray beam. Now, a cathode ray is a stream of electrons from the surface of a cathode and accelerated to the anode by a high potential difference. So in effect, that's essentially what we've been looking at. We've been looking at a stream of electrons being emitted from a cathode and directed towards an anode. But now we're giving it a specific name. We're calling it a cathode ray. So let's have a look at the cathode ray in a bit more detail. So the structure of the cathode ray is shown below. And what we're going to do is we're going to divide it into three parts. The electric gun, which is this section here, the deflection system, which is this system here, and also we're going to divide it into the fluorescence system, which is this part here. You can see that the cathode consists of a filament, a heated filament, encased in a metal. And what happens is that the heated filament causes the metal casing to become red hot. And as a result of causing it to become very hot, the casing emits electrons through thermionic emission. Now those electrons move in a straight line because they're attracted by the positive anodes. These are positive. So the electrons move through this grid and through the anodes, and then they go through a series of plates. So we have here a Y plate, and we have over here X plates. And depending on the voltage across the plates will determine how this beam is deflected, whether it's deflected upwards or downwards, or to the left or to the right. And then when the electron beam actually hits the screen, it interacts with the screen because the screen is a fluorescent screen, and what you'll get is a bright spot. So the electron gun, it emits a narrow beam of electrons, which are called cathode rays. The deflection system, it can deflect the path of the electrons vertically by applying a potential difference across the X plates, and horizontally by applying a potential difference across the Y plates. The fluorescent screen is actually coated with a fluorescent material, so that when the electron beam hits the screen, then light is emitted from that fluorescent screen. Let's suppose that the X plates, they have no connection. In other words, there's no potential difference across those plates. Therefore, when there is a voltage across the Y plate, there's going to be a degree of differences in terms of the pattern on the screen. So, for example, in this case, there's 0 voltage across the Y plate. That means there's going to be no deflection for the electron beam. So the spot is going to be in the center of the screen. Now here in this diagram, what you can see is that there is now a potential difference. But this time it's a constant DC voltage. Remember that DC voltage means that the voltage is applied in such a way that the current flows in one direction. So let's say we have a 3 volt DC voltage across Y plate. That means the deflection for the electron beam is going to be such that it's deflected upwards. So the larger the DC voltage, then the larger will be the deflection. In this case, you can see what's happening. Here we have the same plates, but the difference is that we have what's called a non-constant AC voltage of 50 Hertz. So that's an alternating current. So that means that if that's applied across the Y plate, then what you have is what's called an unstable deflection for the electron beam. The beam is going to be moving up and down. It's going to be alternating. So the spot is going to be deflected upwards and downwards rapidly, and that will form a vertical straight line due to the alternating nature of the AC current. The potential difference across the Y plate, that is measured by the Y gain control, or the gain control. It's calibrated in such a way that it gives you the voltage per centimeters, or voltage per division. So the potential difference can then be found by measuring the deflection of the spot from the center of the screen upwards or downwards. So the X plates, they're connected to a special circuit. This circuit is actually called a time-based circuit. It makes the spot sweep across the screen from left to right at a steady rate. The spot will move back to its starting position very rapidly and repeat the motion. So here we can see that across the screen, because of the nature of the rapid movement, then we have the time-based circuit within the oscilloscope causing that spot to move across the screen. If we look at an oscilloscope, in fact, if we look at these two here, we can see what the patterns would look like on the screen. So here we have a dot right in the center of the screen because there is no connection to the Y plate, there's no potential difference, and there's no connection to the X plate. So again, there's no potential difference. The result of that, when you turn on the oscilloscope, the dot will be right in the center of the screen. Now, if we apply a potential difference across the Y plate, and it's a DC voltage, and there's no connection across the X plate, then what will happen is that the dot will move towards the top of the screen due to the potential difference because of the DC voltage has been applied, so the spot will move upwards. So let's have a look at the patterns here. Here we have a Y plate which has got an AC alternating current, alternating voltage applied to it, and the X plate has no connection. So you can see now, due to the alternating current, that the spot appears to move vertically upwards. Over here on the second monitor, we have no connection on the Y plate, but we do have a connection in terms of a time-based circuit on the X plate. So as a result of that, the beam will move from side to side very rapidly across the screen. Now in this particular scenario, what we have is we have a Y plate and we have a DC voltage across the Y plate, and we also have a X plate where there's a time-based circuit. So you can see how the beam now will be moving across the screen at the top of the screen because of the DC voltage applied. Now in this case, in the second monitor, you can see that in the Y plate, there is in fact an AC voltage. But also there on the X plate, there is a time-based circuit. So what will happen is that will cause the beam to move up and down in a transverse manner across the screen. And that is traditionally how we tend to see alternating current represented on the monitor of an oscilloscope. A little worked example that you may want to have a look at. It says an AC power circuit or an AC power supply is connected to the cathode ray oscilloscope as shown. The peak voltage of the AC supply, and B, what is the frequency of the AC supply. So look at the diagram and see if you can determine what the peak voltage is and what the frequency is. Remember, it's an AC supply, hence the reason why you have this transverse wave across the screen. Video and have a go, and then when you're ready, press play to have a look at the answer to this worked example. Right, the peak voltage is going to be equal to 1 times 5 volts. The period is going to be equal to 4 times 20 milliseconds, which is equal to 80 milliseconds, which is equal to 0.08 seconds. And we can see why that is, because here we can see that vertically the division in terms of each of these squares is 5 volts. And then we can see that in terms of going across the screen horizontally, each of these represent 20 milliseconds per division. So 5 volts per division going upwards vertically, and 20 milliseconds per division going horizontally. So we can work out the period because we have 4 divisions going across the screen, and 4 times 20 milliseconds is 80 milliseconds, which is equal to 0.08 seconds. And the divisions going upwards, we can see that the amplitude, the peak, is 1 division, which is equal to 5 volts. So 1 times 5 gives you 5 volts. Frequency is just equal to 1 over t. So because we know that the period is t, and that's given as 0.08 seconds, 1 over 0.08 will be 12.5 hertz. So let's just summarize what an oscilloscope does and how the oscilloscope functions. We've looked at it in a little bit of detail, so now here is a summary. If we look at the following oscilloscope, you will see that in terms of the vertical axes, we have voltage, and the horizontal axis, we have time. This is a waveform display, and it's shown with grid lines or divisions. And this is the type of example that you would find with most oscilloscopes. They would be set up in this way. And so you have the vertical spacing of grid lines, and these are, in terms of representation, these would be the volts per division setting. So each of these vertical areas or vertical blocks, they would represent voltage. And you can set up your oscilloscope so that each of these particular vertical blocks would have a certain value in terms of the voltage per unit setting. And also the horizontal spacing of grid lines, they relate to the time, and they can be in seconds or milliseconds, divisions, etc. So in other words, you can use the oscilloscope to decide how you're going to calibrate it in such a way to give you the nature of the voltage in terms of the magnitude and also the time. Now, the most common measurement technique using oscilloscope is as follows. We have a ground level, which could be anywhere on the oscilloscope. So let's say, for the sake of argument here, the ground level is set here at 0 volts. Now, if you look at the oscilloscope, you can see that the time period is actually 5 divisions or 5 blocks. So if we take from that particular starting point, we'll go 1, 2, 3, 4, 5. This is where the actual wave repeats itself. So that would represent the time period. So that would be 5 divisions. And you can see that it's actually 1 microsecond per division. So what we have here is that the time period is 5 microseconds. And therefore the frequency is just going to be equal to 1 over the period. So it's going to be 1 over 5 microseconds. And that gives you a value of 200 kilohertz. And in terms of the vertical peak, you can see that if we were to consider peak to peak in terms of the number of divisions, so if we start with this peak and we want to consider the number of divisions between this peak and this peak or that peak, we can see it's 1, 2, 3, 4, 5, 6 divisions. And if each peak is 1 volt per division, then for peak to peak, we have 6 volts. Now the maximum, if we assume that this is the ground level here, so this is the ground level, this line here, then if that is the ground level, then the maximum peak, V max, is going to be 1, 2, 3, 4 divisions plus 4, and that's going to multiply that by 1 volt per division. So that gives you a maximum Vmax in terms of the maximum division, in terms of the value for P max, is going to be 4 volts. Now, V min, what do you think that would be? Well, again, if we start off at the ground level and we look at V min, where this would be the minimum for the peak, then it's 1, 2 divisions. So it'd be 2 times 1 volt per division. So that would give you a value of 2 divisions. And here we have a typical primary oscilloscope, and this is one that you find very similar to this in most laboratories. And you can see that what I've done here is just to give you an example so that you can see what a oscilloscope actually looks like. And they tend to sort of look a little bit like this. This is a more sophisticated modern one, but you can see that you have horizontal scales for the horizontal time in terms of the time per division. You have horizontal positioning, so you can move the actual waveform up and down and position it. You have vertical scale in terms of the scales vertically in terms of divisions in volts, and you can have also a control which regulates the vertical position. So this is a typical oscilloscope, and one that you may come across in your physics labs. So in terms of, again, just summarizing the setup for your oscilloscope, sometimes when you turn the oscilloscope on and you have a signal coming to it, an electrical signal, the electrical signal then is converted into light. You may get too many cycles displayed, and so the amplitude scaled is too low. So what you do, you can actually set up an optimum arrangement whereby you are able to have your waveform in such a way that it is easy to deal with and to read in terms of the x and the y coordinates of that waveform. In other words, the time and the voltage. You can adjust the voltage division knob until the waveform fits most of the screen vertically, so you have that facility. And you can also adjust the vertical position until the waveform is centered vertically. So there's so much you can do with an oscilloscope in terms of manipulating the waveform. If you adjust the S division in terms of the knob horizontally until just a few cycles are displayed, so you can do that to give yourself a more realistic view of the waveform. You can also adjust the trigger level knob till the levels set near the middle of the waveform vertically. Trigger level knob will actually set this up so that this is more or less in the middle of the screen. Now going to have a look at how television pictures are formed. We've looked at how a cathode ray tube works. We've looked at a cathode ray oscilloscope. And now we're going to look at the same principle but applied to television picture tubes. Now in this diagram, what we have is we have a television cathode tube. And here you can see that we have, in terms of describing the diagram, a glass where there's a vacuum, so all the air is being pumped out of that television tube. And we have a screen, and we have a mask in front of the screen, which I'm going to explain what that is a bit later on. And then we have an electron gun with 3 primary colors, which are the red, green, and blue. We have what's called a deflecting coil, which deflects the beam coming from the electron gun. And we have a focusing coil. And as the name implies, that just focuses the beam which are emitted by the electron gun. And then over here on the right hand side, you can see this is a little bit more detailed to show you exactly how the electron gun in terms of the different beams, the blue beam, the red beam, and the green beam, how they are focused onto the screen. And so we're going to talk a bit more about how these beams are manipulated inside the TV picture tube to give you an image. So we're going to have a look at that in a moment. First of all, let's just go through the steps. So the electron gun, one for each of the primary colors, red, green, and blue, they produce rays. An electromagnet is used to deflect the beam. Now, you could also use electric plates. Electric plates, they tend to be quite expensive. Although they're very high precision, electromagnets will do the job. Electromagnets will actually reflect the beam coming from these blue, red, and green colors. Fluorescent screen, this consists of dots, and these dots are of what we call fluorescent paint. So when you get the beams striking the screen, then these particular dots are going to get excited when the electrons strike the screen. When the electron strikes the screen, then what will happen is that light will be emitted by the dots on the screen. Once the electron gun produces cathode rays and they correspond to the correct color, they're going to be focused by this mask, and this is a shadow mask. It's focused by this mask. It then strikes the fluorescent dots on the screen and it gives an image. The image is formed as the beam scans from left to right and from top to bottom. So it's a bit like the X and the Y plates in an oscilloscope. The color of the image is determined by the relative intensities of the three beam colors. This is just a simple sort of explanation in terms of how you get an image on a TV picture tube, and you're not required to go into it any more detail than this at grade 10 level physics.